Okay, good afternoon. I had one question about the exam, and it's a legitimate concern because we lost almost a week. We meet only once a week, and when we lose a week, it looks like we have lost a lot. But I think we will still have the first midterm on the 25th of September and the second on the 30th of October as scheduled, and then the final exam on December 6th. We will see enough material by then, and I think we will restrict to the material that we cover till the lecture before that. Okay, so if we're going to have an exam on a Tuesday, the Tuesday before that, whatever material that we see, we have about perhaps three lectures, and you will get to do 2 assignments by then. Okay, and normally I give a kind of a quiz before the exam to give you an idea of a preview of what the exam might contain, and we may not have the time to do that, but we will see how things go. So as of today, I'm trying to stick to the schedule that I originally put on Moodle. So the first midterm would be on the 25th. And I've reset the clock for the assignment twice now in a row, because the first week I didn't cover as much as I wanted to, so I felt that it's not fair to ask you to struggle through the assignment on your own. But some people have still taken the bold approach of trying to attempt that. In fact, I think 1 or 2 have submitted already. But the first assignment it's as if I handed out today, so it will be due next Tuesday by 4 o'clock on Moodle. You have to upload a single file with your solution, with your answers, onto Moodle by 4 o'clock next Tuesday. And I already made up the second assignment, and I will release it if I have not done it already. So those who want to get ahead, you can take a look at it, and it'll be due a week from next Tuesday. Okay. So any other questions or comments? Yeah. Question, I guess, is what is the structure of the exam? One of the things that we have when we have this discussion is, when I'm trying to record it, you don't hear the question, and so it doesn't really, if you choose to listen to it again. So what will be the structure of the midterm exam? It will be on concepts that we have seen in the class. It will be, the first midterm exam will be very much like your first assignment. A lot of questions, maybe 25, 50 questions, short questions, things like express this number in hexadecimal, or if it is in hexadecimal, express this in decimal. How do you make the conversions? What is a floating point number? What do we mean by class in MATLAB? And then MATLAB related questions, because the whole course is going to be to train you in the language of MATLAB. So if I enter this particular command, what will MATLAB produce? Can you try to figure out what it will be? So that's the kind of thing that you're going to be doing in your assignment, and it'll be something like that, the first one. Towards the end of this course, we will be building it up to a stage where we will see how to use computers to solve engineering problems. So at that stage, we will get into some problems where I will say, okay, here is a table of temperature versus time from a distillation column, and do an analysis on that. We have 2,000 data points of temperatures versus time. What is the average? What is the maximum? How many days was it above a certain temperature? Things like that, analysis of that. So write a small program in MATLAB that will do those kinds of analysis. As I said in the last lecture, sometimes it may be a program I give it to you and say, this program is supposed to do this kind of analysis. Do you think it is going to do it? Are there errors in the program? Fix it. Things like that. Okay? Any other questions? Yeah?
Can we see some examples of e-portfolio?
Have you listened to the e-portfolio that I put on Moodle? What I would recommend is that you list, the question is about e-portfolio. Can I see an example of e-portfolio that I have put together? I don't want to kind of set a low bar by showing what I have done. What I've tried to do in building that e-portfolio that I did using my own data is to show what is possible, how to set up a link to a multimedia device on the internet, how to set up your own link to a file that has your curriculum vitae. But I want you to you have the whole term to do that. You to take a very creative look at how you can do this. And I think all the elements I have shown with using Word as a simple tool. But I know the range of ability varies. Some of you have already seen C++, Java, whatever. So if you can demonstrate a superior ability in building these ePortfolio, basically what you should do is try to impress the person that is going to hire you, for example. So by the time you graduate, you may be wanting to distribute your credentials in an electronic form for people to see. Okay, so that's basically the idea of how to create one and how to upload. Those are the things that I have focused on. So I will not give you a sample right now. Okay, I would like you to take a look at it. You have the whole term. Towards the end, if there are people still struggling, then I'm willing to show and help out so that you set up at least a minimal one. But I don't want to restrict your target. Reach as high as you can. Spending maybe just an hour a week, you may still be able to do a very good job towards the end of the course. But get started early. Okay? So there is a video on Moodle, and look at it. And if you have questions, you can always come and talk to me in my office. From this Friday onwards, because the assignment is due next Tuesday, I will have office hours. I think between 1 and 5, or 1 and 4, and 2 or 5. 2 and 5, I'm not sure which one it is. But it is in the timetable, and you will see that. And I will also come up to the virtual classroom, so if you want to talk to me online, there is a link to the virtual classroom in Moodle. You can click that from your home or wherever, and you'll be connected to my desktop, and we can chat, and I can grab your program or answer questions, stuff like that. So from this Friday, we will have strict office hours. Okay, so let's get started. In the first lecture, basically what we did was look at, talk about in general what a computer is, what are the various components that go into a computer, like a memory, a hard disk, and the input-output functions. And we looked at what are the powers of the current day computers, which are very enormous. 1.5 million computers connected together, acts like a single computer, able to do a petaflop of calculations, 10 to the 12 multiplications in 1 second. So the power is enormous, and what we want to do today is learn a little bit the rudiments of what we mean by bits and bytes. How do we represent numbers in computers, and what are the sources of errors in computing? For example, if it does 10 to the 12 multiplications in 1 second, and each multiplication has an error in the 15th decimal place, and that error propagates every time that you do a multiplication, the error can completely swamp your calculations, and what you get out is garbage. So what you need to know is what are the sources of origin of these errors. So in order to understand that, these are called round-off errors. And to understand the source of these round-off errors, we need to understand how we represent numbers in the computers. And some of this will be very elementary, but then we are going to build from that very quickly to fairly complicated representations. So I'm asking you to generalize what you already know. Okay? I have put a set of links here for in the internet where you can find additional information. Okay? But let's take a base 10 representation. What does it mean? Base 10 means I'm going to use 10 as the basis to represent numbers. That means I'm going to create 10 symbols, and I'm going to use these repeated symbols to represent any number that I want. So what are these symbols going to be? They're going to be 0, 1, 2, 3, 4, all the way up to 9. If you count them, there are 10 symbols. These symbols could be anything that you create, okay? But how are we going to use that to count and to represent numbers that are much larger than those 10 numbers? If you ask the question, why 10? Perhaps we came up with this 10 because we have 10 fingers. We were just counting with the fingers. But if you take a number like 7,354, you all know what it means. When I write that set of symbols, 7354, you know what that means in your mind. How did we come to the understanding? Right from grade 1. Okay, so we know, for example, 4 is in the first position, 5 is in the 10th position, 3 is in the 100th position, 7 is in the 1000th position. So the same way, the same thing that we can write as 7, which is the coefficient that you will find here, multiplied by 10 to the 3. To represent that is in the 1000, 7,000. So that is the same as this. Plus, we can take 3 and multiply that by 10 to the 2 to indicate that it is in the 100th position. That gives you 300. Okay? And then you take the 5. 5 is here, and it is in the 10th position, and that gives you 50, and finally 4. You must be wondering, what is he kidding? Teaching us numbers, arithmetic. The idea that I want to focus on is the use of the bases. What do I mean by the bases? It is 10 to the 3, 10 to the 2, 10 to the 1, 10 to the 0. So we represent this as a linear combination of these bases and then add them up to get 7354. So if I have a decimal, for example, 7354.523, how do I generalize that? In the same way, 7,354 plus all the places that appear to the right of the decimal point. So I put 5 times 10 to the minus 1. If you notice this, it decreases from 3 to, can you see at the back, those little characters? 1, 0, and then what do you see here? Minus 1, minus 2, minus 3. Okay? So 10 to the minus 3 is 1 over 1,000, so it's 0.003. And that's what puts in the third place after the decimal. Similarly, 10 to the minus 2 is 1 over 100, 0.01. That gives you the second place. So this is how we construct numbers based on 10. So are there any questions on that? Now the question that we ask is, can I construct other systems? What is so special about 10? 10 is, as I said, special because perhaps we have 10 fingers. But there is nothing very unique about the process. The question then that I ask is, with computers, what is a natural system to build a number system on? And it turns out to be binary system. What do we mean by the binary system? Anybody? Zeros and ones. Okay? So we need to use only 2 symbols. It could be 0 and 1, it could be A and B, it could be just 2 different symbols. But we need to use only these 2 different symbols to establish a number system. Why do we use only 2 numbers with computers? Because in computers, you have essentially on-off. These are 2 states, binary states, positive, negative, charge, for example, north-south, magnetic charge, magnetic poles, and 0 and 1. Okay? So if you look at magnetic storage devices, we'll just store the north-south as a bit pattern. So that is called a bit. Okay? So you can have billions and billions of bits that are stored in a very tiny place. All the storage devices that are based on magnetic use that kind of a principle. Okay? And if you take diodes, you have semiconductors, current passing and current not passing, for example. These are 2 possible states. So you could use, if you can construct a binary system, then we could use that to represent numbers, to represent other logical operations, to represent additions, multiplication, etc. Just like we developed such a system on a decimal system, we could develop one based on the binary system. But there is nothing unique about binary. It turns out it is very convenient for developing computer systems, but you can also develop octal system based on 8 or hexadecimal system based on 16. Now, if you have an octal system, for example, you can choose your number set to be 0, 1, 2, 3, 4, 5, 6, 7. Just use those 7 symbols to construct all the numbers that we want. And I will show you how that is generalized. And similarly, if you want a hexadecimal system, we need to have 16 different symbols. So what do we do with hexadecimal? We take all the 9 symbols that we know, 0 to 9, and then we add A, B, C, D, E, F. 6 other symbols. So a hexadecimal number will contain any of those 16 symbols, 0 to 9 and A to F. Okay? Whereas a binary will contain only 0 and 1. You can represent any number that we want in decimal in equivalent systems. Do you understand? Any questions on that? And what we need to do is, how do we do that? We need to understand how do we do that the next step. I'm telling you a set of numbers, okay? 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1. Doesn't mean anything to us right now, right? Just a string of 1s and 0s. But this number represents the same number that we talked about, 7, 3, 4, 5. That is the same number. Okay? 7, 3, 4, 5 in decimal system. How is that? How do we build such a system? How do we interpret it? We simply instead of wherever we had 10 to the power something, we have 2 to the power something because we have only 2 states. So the way that we construct our number is using these coefficients as we did with the decimal system, but these coefficients can only be zeros or ones, depending on the position. For example, here I have 1, so I put 1 there. Here I have 0, so I put 0 there. And then I start from 2 to the 0, 2 to the 1, 2 to the 2. I think I have a typo there. 2 to the 3, 2 to the 4, 2 to the 5, etc. Okay? So for each position in this bit pattern as I go, I start numbering from 0, 1, etc., the position. So that is the 12th position. So it is 2 to the power 12. So the number that appears in that position will have 2 to the power 12 as its value. Now I want to make sure that you understand this. Okay? Instead of 10-base system where we cycle through 10 possible representations before we move the digit to the next place, with binary system we can go only 0 and 1. Okay? And then we move to the next digit on the left to continue building higher numbers. How many of you understand that concept? How many of you do not understand that concept? That's very good. Okay? So this number I'm telling you is the same as 7345. How do I know? All you need to do is calculate 2 to the power 12, add it to 2 to the power 11, add it to 2 to the power 10, and then I don't add these because these are all zeros. Okay? So I'm going to open up MATLAB and show you that it is in fact the same. Now how do I open MATLAB? In any lab, you just go and find this icon, the program, and then start the MATLAB. And I'm going to switch between MATLAB and concepts. Okay, so I'm going to demonstrate MATLAB implementation of a lot of these ideas as we go along. So MATLAB is a very interactive environment. I will give you a little bit introduction to MATLAB and the various windows and stuff like that. But let me just show you the calculations right now. So that you see that it comes out to be exactly the same number, 7345, so that you understand that the representation, the way that we break it up, is simply 2 to the power 1, 2, 3, 4, etc., and then we just add them up. Okay, so in this particular example that we have, we needed 13 bit positions, 13 bits of information. So each one is called 1 bit of information, 0 or 1. Okay, so I need to switch between these two. Or if you can remember, or if you have the notes, please help me with that. What I'm going to do is type exactly what I've seen here. 2 to the power 12 plus 2 to the power 11. Okay. 2 to the power 12. This is how I would type it in MATLAB. Power is indicated by the upper caret, okay? Plus 2 to the power 11 plus, I already typed a mistake, please correct me if I do that, okay? 11 plus 2 to the power 10 plus, what do you remember what the next one is? 754, okay. Plus 2 to the power 7, plus 2 to the power 5, plus 2 to the power 4. Anybody else plus?
No, 0.
Pardon me?
To the power 0.
2 to the power 0, plus 2 to the power 0. Let's see. 7, 3, 4, 5. So it just exponentiates that number and then adds them up. So that is a binary representation of the decimal number 7345. Okay? Any questions on that? That is an important concept because we're going to build very quickly on that concept. Okay? So if it already looks fairly complicated pattern, okay, but there is an easy algorithm, easy stepwise procedure to calculate the binary representation. So one of the questions that I'm asking is, what is the maximum number that you can represent if I have only 8 bits? Okay, zeros and ones, but 8 times I can use that. So it is 1, 1, 1, 1, 1, 1, 1, 1, 8 times. How do I answer that question? I simply have to put 1 times 2 to the power 7. Remember, it always starts from 2 to the power 0. So even though I have 8 bits, it starts from 2 to the power 0, so it ends at 2 to the power 7. Okay? So I add them all up, 2 to the power 7 plus 2 to the power 6 plus 2 to the power 5 plus 2 to the power 4, etc. and it turns out it's 255. Okay, so 8 bits happens to be a good chunk of data. Okay, and if you use only 8 bits, these are all the numbers that you can represent. You can't represent any number bigger than 255. Okay, but what you will find is that as you increase it to 16 bits or 32 bits, the range of numbers that you can represent goes up exponentially because it is always 2 to the power something. Okay, with 1 extra bit, how many numbers do you think you can represent? Instead of 8, if you have 9. 0 to 511, which would mean a total of 512 bits. So this goes from 0 to 255. So actually 256 different combinations that we can explore. In the same way, for decimal point, 19.635 turns out to be 1001 point will come here. Okay, 1 over 2. 1 over 2 is 0.5, and that's what gives you 0.5. And then you have 0. This is 1 over 4, and this is 1 over 8. 1 over 2 to the power 3, which is 1 over 8. 1 over 8 is 0.125. So it is 0.5 plus 0.125 gives you 0.625. So that would be the binary representation, but we need to figure out how to pack these numbers. That will be the next thing that we will see. Okay? Okay. Let me give you a few binary numbers and see whether you can figure out what it will be. For example, 1010. If I give you 4-bit patterns with that 1010, what do you think will be its decimal representation? How would you do it? 2 to the 0 plus 2 to the 1 plus 0, right? Sorry, this is 0 times 2 to the 0. 1 times 2 to the 1. Let me erase that. I don't want you to. You have to remember that you have to use the coefficient also. So when I'm going to do a binary, the decimal representation of this, I'm going to take this and multiply it by 0 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 to the 2, plus 1 times 2 to the 3. So 2 to the 3 would be 8. And the next one is 0. 2 to the 1 is 1. So 8 plus 2 is 10. So that will be the bit pattern for 10. Okay, the decimal of this one would be 10 decimal. Okay, do you understand that? Any questions on that?
Can you say that one more time?
Yes. That's very good. That's all I need. Just say it. If you don't understand it, repeat it. And of course, you can always listen to it again also. Okay? So what I'm asking you to is find, if I give you the bit pattern in a binary system, 1010, what is its decimal equivalent? And the way I find that out is by writing the coefficient and multiplying it by from the right to the left. 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. Each one is multiplied by the corresponding coefficient. Okay? 0, it's 0. Do you understand that? So similarly, if I have 0 in the third position, I have 0 there. Okay? In the second position, I have 1, I have 1. In the fourth position, I have 1, I have 1. But they're all multiplied continuously by 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Very simple recipe. Once you have that, then do the actual multiplication. And doing the actual multiplication means this is going to give you 8. This is going to give you 0, this is going to give you 2, this is going to give you 0, that is 10. This would be the type of questions that you might have. I'll give you a bit pattern and say find the decimal. I'll give you the decimal, find the binary. MATLAB has built-in functions that will allow you to do these conversions. I will show you all those also. So what I would like you to do is, well, we said that 10 should have a bit pattern of 1010. Here I have a table for up to 1 to 20. So take some of these numbers and play with by yourself to see whether 16, for example, has the correct binary representation here. Okay, just play with it. And that will reinforce this idea of translating from one system to the other system. Okay? Addition. How do we do addition in binary? It's very simple. If I have 0, 1, 0 and I'm adding it to 1, 1, 1, All I have to do is very similar idea that we do in decimal arithmetic. 0 plus 1 is 1. Okay? 1 plus 1, you flip it to 0, but carry the extra 1 to the next digit place. Okay? So here you have 1 plus 1, so you make it to 0, but carry the 1. And add it to that 1, so that is also 1 plus 1, which is 0. And you carry the 1 to the next place, and you add them up. So it is actually, you can see how easy it is in computers to do these additions. All you need to do is look at the bit pattern and flip them. And you can do additions and subtractions in a very similar way. So you can carry out all the arithmetic operations that we do in the decimal system in the binary system very easily. What we really want to understand from this lecture is how these transitions are done and where are the sources of what are called round-off errors. I want to get up to that point today. So far we have talked about integers. Okay, if you give me an integer number like 25, I know how to represent it in binary form. Okay, we will also see how to represent it in octal or hexadecimal, and we'll see some MATLAB programs that will do that. But before we get to MATLAB, I want to show you another number representation, which is not integer, but it is a floating point representation. A floating point representation simply means a number that has something like 1 point, some decimal places, and then multiplied by 10 to the power something. Okay? Here I have an example, 7634.562. I'm going to represent this in what we call a scientific notation sometime. So I'm going to put one digit, and then I'm going to put a dot there. So I'm going to move this decimal place to this position. So I'm going to write this as 7.634562, but in order to represent the same number, I need to multiply this by 1,000. Okay, 10 to the 3. Okay, so I can always make this rearrangement, and if I can make this rearrangement, I have separated out what we call the mantissa part and the exponent part. This is called the exponent, and this part is called the mantissa. Even if you have a very small number like 0.0000423, I can put a decimal point there after 4.2567, but I need to multiply this by 10 to the minus 5. Okay, so my exponent now is minus 5, and the mantissa is 2567 that comes after the decimal place. So I can always rewrite a decimal number in this notation. What does this allow us to do? This allows us to represent any number, not just integer numbers. Okay, these are called floating point numbers. So it could be, for example, 1 over 3. What is 1 over 3? It is simply 0.33333. That just continues forever. Okay, so I need to then take the fractional part, and I need to take the exponent part and construct a bit pattern for each one of them so that I can represent floating point numbers in computers. Okay. Now, this is a chemical engineering course, and it looks like a computing science course. It really is not a computing science course. All we want to do is get a little bit of number representation so that we understand sources of errors and how they get multiplied. If you do millions and millions of calculations, how quickly they can corrupt our calculation. So in the binary representation, we are going to carry the same idea. If you give me a number and I want to split that into a fractional part and an exponent part and figure out what these fractions and exponents are and then pack them together, and that would be a floating point representation of a bit pattern that corresponds to a decimal number with fractional part. So the binary representation is typically done as 1 point. You see the BBBB here. Those are all the binary numbers by 0101 coding, and 2 to the power. Because it's a binary, it is 2 to the power instead of 10 to the power. And again, you have a bit pattern, BBB, which are zeros and ones that represent a certain decimal part. So we still are comfortable with the decimal part, and that's what we will read. But when we feed it to the computers understand only the binary parts because they can deal with only 2 states. So we have this interchange that is normally transparent to us, but it gives rise to some problems that we need to be aware of. Okay? So if I give you a number as an example, that represent a decimal 50 in floating point representation. You already know how to represent decimal 50 that is integer in the decimal notation, 10-base system, in binary as integer. Okay, the integer representation is simply 110010. I would like you to, whenever you see something like that in the notes, just figure it out for yourself, because that will teach you how to do these things. We'll get better at it, prepare you for the quizzes and exams. Okay? But the floating point representation is going to be in the following way. I'm going to find 2 to the power an integer in such a way when I divide 50 by that number, I always get 1. That is, I want a number that is less than 50, not greater than 50, but the largest number, which is expressed as 2 to the power some number. Okay? So if I take 2 to the power 5, it is 32. So 50 by 32 will give me 1 point some fraction. And I can actually do the multiplication and figure out what the fraction is. 50 by 2 to the power 5 turns out to be 1.5625. But what I have really done here is multiply and divide by 2 to the 5. So I have not changed the original number. The original number is 50. I multiply by 2 to the power 5. I divide by 2 to the power 5. So that the number remains the same. But then after having done that, I regroup these two numbers separately. That is 50 over 2 to the power 5 multiplied by 2 to the power 5. And 50 over 2 to the 5 is that 1.5625. Multiplied by 2 to the 5 I keep as before. Why would I want to do that? Because I want to express the original 50 in terms of a number that has this pattern. This is my floating point representation inside computers. It should be 1 point a bit pattern, 2 to the power a bit pattern. So now I have obtained 2 to the power a bit pattern. It is 2 to the power 5. And I have obtained here 1. So I need to figure out what is the bit pattern for 0.5625. I need to figure out what is the bit pattern for 5 also. Okay, so you know for 5 the bit pattern is 101 in binary form. Okay, and for 0.5625 the bit pattern is 1001 after the decimal point. Am I going fast?
You won't be able to figure that out for the exams. So you have to get about 65.
Yeah, that's a very good question. Okay, first I want you to understand the process that we are going through. If I'm going fast, you need to slow me down. Okay. The next question is, should I be able to do that? Here I'm trying to illustrate with an example. Say, if you are given 50, the first question that you need to ask is 2 to the power what will give me a number that is lower than 50? There is a trial and error process. You'll, for example, take 2 to the power 2, 4. 50 by 4, that gives you a number bigger than 1, right? Then you will say 2 to the power 3, 8. That also gives you a number bigger than 1. So you keep incrementing it until you find 32. So 50 over 32 gives you 1 plus a fractional part. That's when you will stop. That's how you figure out when to stop finding the exponent, 5. That's your question, right? Are you guys following? Now you said I'm going fast. So till what point should I roll back and repeat? Are you following so far? Or
you did examples going from ones and zeros to numbers,
yeah.
Never from numbers to ones and zeros.
Right, I did not because I'm going to show you a MATLAB function that allows you to go either way. Well, since you asked that, I will show you that MATLAB function right now. Okay, that shows you to go both ways. Now, when MATLAB function does that, it has a rule, it has an algorithm. What is that rule? I told you the rule for going from binary to decimal. But I did not tell you the rule for going from decimal to binaries. But you can kind of, if you have to create this, how would you do that? If I give you a number like 25 and I say find the binary bit pattern for that, you know, yeah.
You explained how you went from 1.565 to 1.1001?
1.1001? Yeah, I will explain that after I come to this question. The question was, I showed you how to go from a binary bit pattern to a decimal bit pattern. Okay? So if I give you a bit pattern like this, for example, how do you go to the decimal representation? You will just take 0 times 2 to the power 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2. That is the sequence. So that's fairly easy for all of you to do, right? And then you do 2 times 2 is 4, plus 2 times 1 is 2, that's 0, this gives you 6, which is what this number is, right? All of you should be able to do that. What I did not answer, did not explicitly lay out an algorithm is how to go back. If I give you 25, what is the bit pattern for 25? What you need to do is reverse the process. So you will have to write something like some number multiplied by 2 to the power 0 plus some number multiplied by 2 to the power 1. These numbers are going to be only zeros and ones. You need to fill those out, whether they are zeros and ones, okay? Plus some number times 2 to the 2, continue on. So 24. So 2 to the power 3 is 8. 2 to the power 4 is 16. 2 to the power 5 is 32. So you don't want 2 to the power 5. You already know that. So you're going to have at most 2 to the power 4. Okay, so continue this. 2 to the power 3 times 2 to the power 4. Do you understand that? So now 2 to the power 4 is 16. So I need 16. Right? So I put 1 there. That means I have, after 25, I have counted 16. What is left then? 9, right? So I need to find what is the next factor I should keep in that. What would give me 2 to the power 3? Would give me 8. So I can put a 1 there. Right? So that's going to give me now 16 plus 8, which is 24. How about the next one? 1. Now, I think I told you, I have a bad habit of, if I hear the right answer, I'm assuming that everybody is following, but I want to make sure that everybody in your mind, as we are going through this thought process, understand how we fill this. Is that clear? If you're given an integer number, we said, okay, I need to find a binary representation of that, and the binary representation now turns out to be something like 11001. 11001. How did we figure that out? We just took as many bits as we need to represent the highest number. Okay? So if I have 2 to the power 4, that gives me 16. 2 to the power 5 gives me 32. 32 is already bigger than 25. Okay? So I don't need the 6th bit. I need only 5 bits to represent this particular number. And then I start filling. If I have 2 to the power 4, that's 16, so I put 1. From 25, I subtract the 16, I'm left with 9. So out of the 9, how do I construct the remaining bits? If I put 1 here, that gives me 8. 2 to the power 3 is 8. Okay? So I put 1 in the next position, and then I'm left with only 1. So I put 0 and 0, and in the last position, if I put 1, 2 to the power 0 is 1. So I get the 25. Right? So what is more important for you is to understand that there are 2 representations, and there is an equivalence, and there is, as an engineer, we are going to use programs that are available for us. We don't have to do it manually every time. But I will test you once or twice in an exam or a quiz to be able to do these translations for very simple situations. Now, your question was, how do I get 0.5625 to represent 1001? Okay? How did I find the binary representation of the decimal part? How would I do that? Can you help me out? 2 to the, so I will have 2 to the minus 1 plus some factor I need to put, 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 4, etc. So if I put 1 here, I get 2 to the minus 1. 2 to the minus 1 is 1 over 2, which is 0.5. So I already have 0.5 there. Okay? So once I subtract 0.5, what am I left with? 0.0625. Okay? So if I take 1 over 4, what do I get? 0.25. What should the digit be for that? 0. Again, everybody make sure that you understand it. Okay? So that's how I get the second 0. I got the 1, I got the 0. 2 to the 1 over 8. 0.125. Okay, so that's going to be 0 also, because if I add that, it's going to be a bigger number, right? And then I have 1 over 16, which is going to be 0.0625. So I need that. That's how I get 1001, which represents 0.5625. Does that answer your question? Who had that question, right? And similarly, 5. 5 is 101. The binary representation of that is this. So the floating point representation of this number 50 is going to consist of this bit pattern and the exponential bit pattern. So we're going to pack them into one, what we call in computer language, a word. Okay? And this is either single precision or double precision. So I have a few other examples. I want you to work through them. Make sure that you understand how to get from 3125 to this bit pattern, or from 10 to that bit pattern, etc. Okay? Let's just move on because I'm kind of running out of time. I want to cover a few things. So this is how I tend to pack the two pieces of information that I have found for the floating point representation of any number. One is the fractional part, which is called the mantissa. The other one is the exponent part. Okay, so I'm going to choose arbitrarily, and this was done by IEEE, Institution for Electronics and Electrical Engineers, very early before the dawn of computers, to come up with a standard. Okay, so these are called IEEE standards for floating point representation, and we choose arbitrarily to use 23 bits to represent the mantissa part and 8 bits to represent the exponent part, and then remember I have sign, plus or minus. So I use 1 bit to represent the sign. So I have a total of 32 bits. If I use 32 bits, it's called single precision. That idea you need to know, because you'll come across, and I'm doing this calculation, it's done in single precision or it's done in double precision. Double precision simply means I'm going to use 64 bits in total. Of those 64 bits, these are 64 zeros and ones packed together, but taken and interpreted in a particular way, they tell us how to find the corresponding decimal representation of that number. So here is a bit pattern, 0, 1, 1, 1, 1, 1, 1, 0, 0, etc. that represents 0.15625. And I would like you to again try that, and if you don't understand, come and see me. If you understand it, it's a confirmation that you have understood the process that we're talking about. Okay? And similarly for double precision, out of the 64 bits, we use 52 bits for the mantissa, 11 bits for the exponent, and 1 bit for the sign. Okay? So we are able to represent larger numbers in double precision to a greater accuracy. Okay? With 23 bits, we can only represent 7 decimal places accurate. Anything beyond that gets truncated, left off. Okay? So if I have, for example, 1 over 3, as I said, or 1 over 9, these are numbers that just repeat for infinitely. But if you're trying to represent them on the computers, we can choose to represent them either to 7 significant digits in single precision or 14 significant digits in double precision. Everything else is forgotten in the computer representation of such numbers. And that is the origin of the so-called round-off errors in calculations in computers. Okay? And in predicting, for example, Isaac, the Meteorological Association will run computer simulations for days, doing billions and trillions of calculations. Okay? And if these kind of errors get into that, repeating that multiplication and division with erroneous numbers will propagate your errors. So we need to manage how the errors are propagated. And that's one of the reasons why we need to understand what these representations are. These are called floating point representations. They are implementations of number representation in a partial sense. We choose arbitrarily to cut to either 23 bits or 52 bits in mantissa, either 8 bits or 11 bits in the exponent in the single and double precision numbers. What does this mean? It simply means that the largest number that I can ever represent in MATLAB or in any computer, okay, that uses 32 bits or 64 bits, for example, these days the processors themselves are designed. I'm sure most of you have come across, this is a 32-bit processor, this is a 64-bit processor, right? So the idea is a 64-bit processor can handle 64 bits of chunks of information at a time. So in a 64-bit machine, double precision, the largest number that you can represent is only about 1.8 times 10 to the power 308. That's a large number, 308 zeros, right? 1 followed by 308 zeros. That's a fairly large number, but computers cannot represent number larger than that. Okay? And similarly, on the left side, so this is your 0. And this side going to plus infinity, and this side going to minus infinity. That's a real line. There are numbers on all those lines, and what we are saying is with computers, the largest number that we can represent is only 10 to the 308 in double precision. Okay? And on the left side, it is minus 1.8 times 10 to the 308, the smallest number. But if you're talking about the number that is closest to 0, that can be only something like 2.2 times 10 to the minus 308. Okay? So anything below that will be considered as 0. Now, 10 to the minus 308 is an extremely small number. What is that number? It simply says 0.000000 up to 308, and then there is a digit beyond that, right? So that is an extremely small number. But the numbers in here and the numbers beyond that and beyond that, we cannot represent on computers. Okay? If you have to represent a number that is smaller than that, you need to use a special algorithm or something, or devise a new computer that can handle 128 bits. The other thing I think that you would have probably come across is in encryption algorithms. If you ever do banking, for example, right? When you're connecting to the banking site, they will use something called HTTPS, right? A secure site. And they will use an encryption algorithm using 128 bits or 256 bits. These are a particular bit pattern that is 128 long, and that is shared between you and the computer when you are doing the transaction. So everything that you sent is encrypted using that bit pattern. Only if the other side knows the same bit pattern, they can unpack that and figure out what the actual information is. So basically what you should know from now is, what do we mean by a bit, and how do we represent integer numbers, and how do we represent the floating point numbers, and what are the maximum and minimum limits. So let's go to MATLAB and see whether we can find some of the functions. For example, here I've indicated real max and real min. These are functions built in MATLAB that will tell you what are the actual values. Okay? So I can type, for example, real max. So it says the largest number that you can represent, a real number, is only 1.7977 times 10 to the 308. So real min. Okay, so that is the smallest number. And we talked about the conversion from one to the other, right? So there are functions like decimal to bin. Let me just type help, DEC to bin. So if you type help on any function, it will give you a brief description of what that function does. So there is a function called DEC, it stands for decimal, to bin, binary. Okay? So this converts any decimal number to a binary bit pattern. Okay? And it tells you should read, okay, it says convert decimal integer to a binary string, returns the binary representation of D as a string. D must be a non-negative integer smaller than 2 to the power 52. Okay? Let's just throw some numbers at it and see. In fact, there is an example here. Decimal to bin, I want to say 2045. So what is the binary representation of that number 2045? It tells me the bit pattern. Okay, 111111101. Obviously, you can guess that there must be an inverse function. What do you think it will be called? Bin to death, right? In fact, it tells you. There is another function, see also bin to death. So if you put a bit pattern, it's going to convert that into decimal. Okay? So I can take, for example, bin to death, and I need to put this as a string, 10111010. That turns out to be 90. So you really don't need to do it manually because there are tools that are available for us, but you should understand the concept and be able to do it for simple cases to demonstrate that you have understood it. Any questions? Yeah.
Yeah, for the first one, for the decimal to the binary, you did put
That's a good observation. These are the things that you learn by observing, by playing with it, and learning to read carefully the inputs. Here it says returns a binary representation of D as a string. So when it returns, this pattern 1001 is actually returned as a string of characters, but it is the binary representation. So when you input, the reason is The natural world for MATLAB is, if I enter 45, what does it interpret it as? It doesn't interpret it as a binary signal, it interprets it as a decimal signal. If I put 01000, it does not interpret it as a bit pattern. So what do you think this will interpret, MATLAB will interpret that as, if I type something like this? It will drop out the leading 0 and it will take it to be a number of 1,100,000, something like this. So its natural state is it interprets everything as a decimal base. And so if you have to represent anything as a binary, you need to put it in quotation marks. Okay, that's a very good observation, very good question. You need to be a keen observer as you make errors to figure out. So I'm going to make a deliberate error and ask you to find out what I did. What do you think it'll do if I type this? It'll give an error. Why?
That doesn't make sense.
It doesn't make sense. If you say bin, it expects a binary number. Binary number cannot have a character 2 and 3. It has to have only zeros and ones. So it says binary string may consist only of characters 0 and 1. Okay? Any questions on that? My God.
On the assignment, it asks us to convert from hexadecimal to binary. Do you want it as like the bit pattern or like 1 times 2 to the 10 plus?
No, the bit pattern is fine. The bit pattern is fine. So I think we're almost out of time, but I want you to make the attempt at the assignment. We have done enough for you to be able to do the first assignment. We are going slower than what I anticipated in both the lectures, but we will see how we can speed that up. Okay?